In this video, I'm going to go over graphing radical functions, specifically the square root function as well as the cube root function. Now, the nice thing about this video is that actually you should know these as two of our parent functions from the very first unit. So I'm hoping as we go through this, it'll start to feel more like a review as opposed to learning something new. All right, so for the parent square root function, let's put in the OG points of 0, 1, 4, and 9. When we take the square root of those, 0, 1, 2, and 3. So go ahead and plot those here. The original, 0, 0, 1, 1, 4, 2, and then finally 9, 3. And hopefully this looks familiar to you from our first unit. Okay, so the anchor point in terms of that h and k is 0, 0 for the parent function. The x-intercept and the y-intercept are both 0, 0. The domain is going to be from 0 to infinity. You'll notice my 0 is included, and the range is also from 0 to infinity. Where is it increasing? The y values are actually increasing over the entire function, so from 0 to infinity. And then for where is it decreasing? It's actually never decreasing. Okay, the y values start at 0, and they're going to slowly keep getting larger. Okay, just a quick review of our transformations. Remember, if you're talking about on the outside of the radical, we're going to be talking about a vertical stretch or compression or shrink. If it is, if you're changing on the inside, like adding or subtracting on the inside of the radical, that's going to move it left or right. Got to make sure you think opposite here. For the vertical translation, so shifting up and down, that's just the number, usually at the end. You can kind of get tricked if they put it in the front, but I usually put it at the end. Adding and subtracting, plus is up, minus is down. All right, and then we will have one, I think, where we have a vertical reflection or flip, okay? All right, so let's look at doing this first example, example 1, using our OG points and then moving them around. So we have 0, 1, 4, 9, 0, 1, 2, 3. I'm going to put the original. You don't have to, but I like to put the original to see how it's changing. All right, so there is the original. And then my new one, right? So if I look inside, I have that minus 4, which means that's going to be 4 to the right. So 4 units to the right for that horizontal shift. And then this minus 2 after it is going to be 2 units down for the vertical shift. So when I put my new function, I'm going to put 4 to the right, which is plus 4. So notice that, think opposite. And then minus 2 for the new y values. So this is going to be 4, 5, 8, and 13. My new y values are negative 2, negative 1, 0, and positive 1. All right, so let's plot the new one here. So my anchor point is 4, negative 2, then 5, negative 1, 8, 0, and then 13, 1 is actually off the grid here. I'm not going to be able to get there with this one. All right, so the anchor point, as I said, was 4, negative 2. That's that horizontal and vertical translations to get those two numbers. The x-intercept looks like it's 8, 0. The y-intercept doesn't have one, right? There is none. We're never going to intersect the y-axis. The domain is 4 to infinity, and the range is negative 2 to infinity. All right, so where is it increasing? It's increasing the entire domain from 4 to infinity, and just like before, it's never decreasing. Okay, all right, let's talk about the cube root function, or the cubic function. Again, this is one that we should hopefully know from that first unit. Our OG points, we're going to have negative 8, negative 1, 0, 1, and 8. When I do the cube root of those, I get negative 2, negative 1, 0, 1, and 2. So I'm going to plot that original one. Oops, that's the wrong spot. There we go. And then I have, just ignore my dog. So I'm going to make the cube root function here. All right. And then for my anchor point, it is 0, 0. The x-intercept is 0, 0. Same with the y-intercept. The domain is all real numbers, right? You can see we're going in all the left and right forever, and range also, all real numbers. Essentially, when you have that odd index, you can plug in any number you want and have no issues. Even index, that's a different story. Where is it increasing? It is actually increasing the entire time from negative infinity to infinity, and it's never decreasing if you move from left to right. Okay, these are the same transformations we just looked at, and so now let's move them around based on our work from the first unit. So in this one here, I am going to look at -1 inside. That's 1 unit to the right. Then I'm going to look at the outside. It says +2, which is 2 units up. You can hear my son in the background playing a made-up baseball game. Just try to ignore it. I'm going to put the parent function on here. -8, -1, 0, 1, and 8. The cube root of those we just did. I'll plot that on there because I like to put the original. All right, and then we're going to move this 1 to the right and 2 units up. So I'm going to, for my new table, I'm going to add 1 for 1 to the right and add 2 for 2 units up. So that's going to be -7, 0, 1, 2, and 9. And the new y values are 0, 1, 2, 3, and 4. Okay, so let's plot that. So -7, 0, 0, 1, 1, 2, 2, 3, and then finally 9, 4. All right, so it should look exactly the same, just we've moved it 1 unit to the right and 2 units up. Okay, so our anchor point is that 1, 2, right? Basically look at your shifts that you did. The x-intercept is -7, 0. For the y-intercept, it's 0, 1. The domain and range will be the same, negative infinity to infinity. And just like before, it's increasing the entire time. From left to right, the y values are getting larger, never decreasing. Okay. Now, I'm going to do a couple more examples where we're actually going to write the function based on some words and based on graphs. This is probably, I think, the trickiest of the two. I'm not saying that graphing is necessarily easy, but if you put in the work to memorize your OG points as well as how to do the transformations, that gets pretty, straightforward once you learn it. This can be tough. So let's look at the example 3. We have our parent function, the square root of x. We're moving it 5 units to the left. It's stretched vertically by a factor of 3, and we're doing 20 units up. So here's how I write it. We know that if we're going to be moving left to right, that's inside. So I'm going to put to the left and think opposite of that. Right? So the left is moving in a negative direction. So the opposite of that I'm thinking is +5. 20 units up is going to be +20 for that vertical shift after the radical. And then the vertical stretch by a factor of 3 means at the very front I need to put a 3. Okay, so this is the answer for example 3. Let's do example 4. All right, now remember the anchor point, right, was 0, 0 for our original, but looks like the new anchor point is at 2, 3. So I'm thinking that's 2 units right, and that's 3 units up. All right, so the way I'm going to think of this is for my for my function f of x, I'm going to put 2 units to the right is -2, 3 units up is +3. But you probably can already imagine, if that's how it was, it would actually look like this, right, if it was just that. So if you notice, we've actually reflected this over what is called the x-axis. I know it doesn't actually go over the x-axis, but if you imagine, right, this is splitting that kind of parabola that I made, right? We're reflecting over in a direction where we're going to flip it over the x-axis. So we're going to put a negative out in front. What I'd recommend, right, if you like, oh man, I don't know if this is correct. What I do to check my work is I always just pick, you'll notice we have points here. We have these points here we can plug in. So like if I plug in 11, I'm hoping to get 0. So let's try 11. All right, 11 minus 2 is 9. The square root of 9 is 3. The opposite of 3 is -3. Plus 3 is 0. Let's do one more for good measure. I'll do 3. The opposite of 3 minus 2. Let's see, 3 minus 2 is 1. The opposite of 1 is -1. plus 3 is positive 2, which is right there. All right, so this is the answer, but I always tell students just plug in to see if you get the right thing. Okay, last one. All right, this is the cube root function. I do know that because I see the parent function here. All right, I do notice that our anchor point is not 0, 0, it's 4, 0. So 4 to the right. All right, and then what I notice is for the original, right, we have 0, 0, and then 1, 1. But if you look here, I don't see 4, 0, and 5, 1. My next point is 12, 1. All right, so what I'm going to do is I'm going to write my new function is the cube root of x. I'm going to put minus 4 for that 4 to the right. I'm not moving up at all or down, so I don't have anything after. But what I noticed is that I have to increase slowly or slower. So that means I'm actually, what we do, this is called a vertical compression or shrink. So I'm going to put a 1/2 in front. You might be wondering, how did I know that? Well, you can always plug in this point, 12 comma 1 if you want, right? You can put an a there like we did in when we did polynomials, and you could put the y value of 1. You could plug in that 12 for x, and we could solve for it. So that's going to be a times the cube root of 8 equals 1. Cube root of 8 is 2. And then you'll see where I got that 1/2. Divide by 2, you get a is 1/2. All right. What I do is I usually just kind of guess what I think it could be. All right. But you have the work there. You can solve it. And then I plug in at the end. So I'm going to plug in 12 to see if this works. The cube root of 12 minus 4. So that's going to be 1/2 times, let's see, 12 minus 4 is 8. The cube root of 8 is 2. And I get 1. And you'll notice the y value for that point is 1. So this works. All right. Anyway, check out the homework. Come see me if you have any questions. Good luck.